Yeah, thank you very much for inviting me to speak in this conference. It is a very nice conference. So the plan for today, I have two talks. So the first talk will be probably just be spent talking about Jacobi forms and quasi-Jacobi forms and trying to make this setup this rigorously. And then in the second part of the talk, I will come to the holomorphic equations where they show up very naturally. So for the start, I think we didn't see this definition properly yet in the previous talk, so I just wrote a complete definition of what is a weak Jacobi form. So essentially, it's a function on the upper half plane times c to c, which satisfies the transformation property under the Jacobi group. So the Jacobi group is the semi-direct product of S and Z, and then there's always the question in which how the design is put. This I very likely will do wrong. So you have this group here acting on this space, the Z2x by translation. So here you have a tau. So maybe I should write a C. So the tau defines your lattice in this C here, and then the C squared here just acts like by translation by this lattice. Okay. So the second of the transformation properties just means that the invariance or equivariance of your function with respect to shifting your Z parameter by a lattice. Okay, so this tau here defines your lattice in your Z plane. So, and here's 0, 1, and then the second equation just tells you how phi changes if you add the lattice.
What's E? E or the E of
yeah, E. Very good. Thank you for the question. So E is and this is what I forgot. So E is just to the 2 pi I x. Just a short term for this. So now this talk probably 2 pi I would just be 1, but yeah, there would be probably 2 pi I errors in this talk. But
maybe you can try to speak a little bit up for the recording, or if not, we can use the mic.
Microphone is better, I think.
Okay.
So the second one is very naturally tells you that this phi defines the section of a line bundle on the associated elliptic curve associated to this. And then the first equation tells you how phi changes under changing the complex moduli. So this came up in Andre's talks yesterday also, how this kind of type of equation. And then the second equation tells you how regular the function is. And here the key is that phi should be a holomorphic function on this space, and then it should also extend nicely to infinity, where tau goes to I infinity. So this is the locus where Q goes to 0. So it extends naturally to Q equals to 0. Oh. Okay, we can try the microphone. Yeah. So this is the weak Jacobi form. Weak Jacobi form means that there's no condition on this R. If you want an actual Jacobi form, you have a condition here between the n and the R. Okay, something like 4n R squares positive.
Did it work? Just keep going.
Okay, so I hope you don't get distracted. So let me do some examples. For the start, maybe the first example you can think about is if you just put m equals to 0. M is the index. So if you put m equals to 0, you see that the second equation here just says that phi of z plus lambda tau plus mu is phi of z. That means that in the first variable it's a bounded function. It's a holomorphic function which is 2 variable. It's bounded, so it has to be constant. So it tells you that phi of z tau is just the function of the single variable tau. And then if you look at the first equation here, this term drops out, and so you just get exactly the equation for modular form. Okay, so this tells you that modular phi is modular of weight. Okay, so if you let j Jack Km will be my notation for the vector space of Jacobi forms of weight K and index M. And that's a finite dimensional vector space. And so then this tells you that the Jacobi form of weight K and index 0 is just the space of modular forms.
Let's give it a time.
Okay. Hello, hello. Hello. Okay. Okay, so this is the easiest example. So, and I hope everybody is somewhat familiar with modular forms. The second example, in some sense, we already saw before also. So let's think about the theta function. So this is the, let's say the odd Jacobi theta function. So this is just defined as the sum of the half integers. And then you average over the half integers. So you have a sign here, and then you can have 2 to the q, and then 2 to the. And this is the function which kind of motivated this term Jacobi. So here the reference is a book by Eichler, I believe. And so if you study these functions, you can observe following transformation properties for the function. I'll put this here. Let me try to make this. Yeah. The first one is if you change the z by a lattice point, then you just get minus q to the minus 1/2 e to the minus 1 theta of z. That's actually easy to prove because you just switch some indices. The interesting equation is this one here, the z over tau minus 1 over tau. And there you get the square root of tau divided by I times e to the pi I z square over tau times the function. So then there's a last, maybe one more here. You can all read them up somehow. So this is e to the pi I tau. So it's not exactly a Jacobi form, but almost. So in fact, what you can do is let's define a normalization of this, which is slightly better. So let's say we take this function divided by the third power of this Dedekind eta function. So and then if you take the square, this will define your Jacobi form. So this will give you a Jacobi form of index minus 2 and weight minus 2 in index 1. And so you can take another one, which is just taking this phi minus 2, 1 and multiplying with this Weierstrass elliptic function. Okay, so the Weierstrass elliptic. If you have seen it, it's nice. If you haven't seen it, it doesn't matter. Okay, so anyway, so and then in some sense, these two things are all that you need. So the algebra of modular forms is really generated by these two modular forms G4 and G6, the Eisenstein series of weight 4 and 6, and then the Jacobi forms of even weight. Let's say of even weight, yes. It's just generated freely by the modular forms that you have. And then this two series. And if you also want to include odd weight, you have one more generator which satisfies some conditions. And so that's my second example here, the second thing to know about it. And then the third thing is this relationship to elliptic genus that we saw yesterday, that if this elliptic genus was defined by this, essentially by the following thing. Okay, so here the xk are the Chern roots of your complex manifold M, complex manifold M. And then the theta here is this guy theta. But the normalization really doesn't matter because we, whether you take this theta or this theta, it doesn't matter because we divide by it. And so then the claim is that proposition, and this was done yesterday, that this is a Jacobi form of weight 0, so a weak Jacobi form of weight 0, and then the index is the dimension of M half if M is Calabi-Yau, if M is compact Calabi-Yau. So of course, if the dimension is odd, then this tells you that this elliptic genus should vanish. Okay. So if you think about dimension 1, then you have a elliptic curve, and then there are no Chern classes. So then, in practice, this is true. Are there any questions? So in some sense, model forms, Jacobi forms are as nice as model forms. That's just a finitely generated ring, 3-4 generators in the Lotter structure. So I erased the middle board now. Okay, so I want to come to quasi-Jacobi forms, which is was my original starting point for the lecture.
So for every Calabi-Yau manifold with odd dimension, the elliptic genus vanishes.
Yeah.
Okay. So for all Calabi-Yau manifolds.
Let me see, think about this correctly. They should not be correct. Yeah, so maybe I'm saying something wrong because so maybe I wanted to make a comment. So, so it's true. So you can if M is compact, manifold, and dimension is even. So if you have odd manifold, then it would be a Jacobi form, but with respect to a character defined by the theta function. So So sorry for this comment.
But okay, for dimension 1 is true, but
for dimension 1 is true, but for 3/4 is.
But this means that. But so this has to do with the fact that the ring is not anymore freely generated. I mean, okay, probably.
No, it has to do with that you get something out of this theta, odd power of theta somehow. So this will be odd power of theta. So in the Calabi-Yau case, it will be odd power, dimension of m times something which is meromorphic Jacobi of index 0. And so if you have an odd power of theta, you get a character in which comes from this transformation properties of this theta. So it's a Jacobi form, but with respect to a character. That comes from the theta. Yeah, sorry for this.
So you will have in mind Calabi-Yau for faults like previous lecture, or just even dimension?
I mean, it doesn't matter for this talks. I mean, I will not talk about elliptic. Genus is just an example where they show up. Definition. So let me define you quasi-Jacobi. Okay, so and essentially the first definition we have to do is, and I will try to do this really rigorously. So it's almost. So we define it as almost holomorphic Jacobi forms, and then as the first we define almost holomorphic Jacobi forms, and then we define the quasi-Jacobi form as constant terms of almost holomorphic Jacobi forms, or the modular parts of this almost holomorphic Jacobi. So almost holomorphic Jacobi form forms of this weight k in index n. It's a function, so it's a function. And now I use big phi because the holomorphic term will be our quasi-Jacobi form. So we function again from the same space, and such that the two properties holds. One is as before, same transformation property, but you weaken this regularity assumption. and the way you read it is you say it's a sum. So maybe I use A, B. Let's say function, maybe I and J. Functions I and J, and then you have a ham times u to the I, alpha to the J, and let's say I normalize this. And so here nu of tau is a non-holomorphic function, so it's 1 over 8 pi times the imaginary part of tau, so it's not a holomorphic function. And alpha is just the imaginary part of z divided by the imaginary part of tau. I has that form. If only finitely many of this phi ij are non-zero, with phi ij non-zero, or finitely many j, so that's just really a finite sum. And then each phi ij, each satisfies this condition 2. Okay, so this is our condition 2 tilde. And so then the definition is the quasi-Jacobi form of this weight in index of a k in index m is a holomorphic function. So it's a function I from c plus h to h c such that they exist in almost holomorphic Jacobi form of the same weight in index phi. No, it has to be alpha j. Such that phi is equal to this phi 0. And so, so if you again, if you have, so I will write out Jack for the vector space of quasi-Jacobi forms. Again, you can show it's a finite dimension vector space. And as before, you can show that if you take k comma 0, so index 0 quasi-Jacobi forms, you just get the quasi-one. So so let me just do 2 examples here. To give you examples of this quasi-modular forms. The first of quasi-Jacobi forms. Maybe the first one I can give us a definition example of a quasi-modular form. So if you take, let's look at this discriminant function, discriminant modular form. So the modular form of weight 12. And so now if you take, so in particular it satisfies this transformation property. Okay. Now let's do something which is forbidden in the world of modular forms. And let's take the logarithm of this thing, and then take the derivative with respect to tau. Okay, so here d tau will be my 1 over 2 pi I over d tau, which is just also q d. If you do this, then you have to think a little bit, because here you have to take a derivative of an argument with minus 1 over tau, which gives you 1 over tau squared. But if you do this, then you end up with d tau of log delta of minus 1 over tau, 1 over tau squared is equal to, if you take this guy here, take a log, you have a 12 times log t. If you take a derivative, at 12 divided by 2 pi I times 1 over tau. And then here you get the same guy. Yeah. Log delta. Okay, so if you define d2 of tau to be a d tau of log of delta, and let's say we normalize this as g2 is minus 1 over 24, and then we end up with. No, I'm erasing this part.
That's fine. Yeah, we'll show you one day.
I'm just warning.
You're asking.
Not asking warning. Okay, so then you end up with this G2 minus 1 over tau. You put this over and you have to multiply with minus 1 over 24 here. So you end up with minus 1/2 1 over 2 pi I. So let me just write minus 4 pi I tau, and then plus the G2 of tau. And so now we have this nu of tau, which is our 1 over 8 pi imaginary part of tau, and then you can check this that this is exactly tau square. So here plus tau square. Tau square nu, and then here we get exactly plus tau over 4 pi. And so this tells you that if you take G2 hat, which is just G2 plus this nu of tau, you get this quasi-modular form. Sorry. You get this almost holomorphic Jacobi form of weight 2 and index 0. And so then G2 here will be quasi-Jacobi form of weight 2 and index 0. So I guess this is. So let's do the same thing for the theta function. Okay? So we have, let me rewrite this argument for this theta function. 1 over and z over tau, and then minus 1 over tau. And we had the transformation property of the theta function, which was this square root of tau divided by I, and then e to the 2 pi I z square over tau and theta of z. And so let's take dz composed with the log. So dz here, dz would be also just would be the same 1 over 2 pi I times d over dz, which will be p ddt. So do the same thing here, dz composed with log to this equation. Then you, and let's call this, a of d tau. Let's call this dz theta of z over tau divided by theta. Okay, so this is the log dz applied to theta. So if you do this, then you end up with a of z over tau 1 over tau is equal to. Okay, so if you take the log of this expression on the right hand side, you just get a sum of 3 terms. The first one doesn't depend on z, so we can ignore it. The last one will give us what we want. Here we also have to think about that we take the interior derivatives, we get a 1 over tau. And then, so the last one will give us what we want. And then the middle one, let's think about the middle one. So that is hard to do now on the board, but if you take the log of this, you get a 2 pi I z square over tau. And if you take the derivative back to this, respect to dz, so you divide by this 2 pi I and you end up with 2. And now you take the derivative back to z, this gives you a 2z divided by tau. 2z divided. hope I got this correct. Maybe there's a divide. I have to divide that. Oh, sorry. So this was a pi. Okay. So in its origin transformation property is pi I z squared. So I have this one, and you get a 1/2 here. So in the end, you get a plus.
Can one uniquely and algorithmically obtain the almost holomorphic Jacobi form if you are given a quasi-Jacobi form?
Yes, I will come to that. So yeah, and first in the example cases. So you just multiply by tau, and then you get z plus this thing. And similarly, you can check that if you take this alpha and you do this change here. So alpha was the imaginary part of z divided by the imaginary part of tau. This would be just alpha z mod tau. And then you get tau times alpha minus here's it. Okay, so you see that if you take a hat, take a plus alpha. This is not, it's not in this ring because this ring has this holomorphicity condition. This a has a pole at z equals to 0. But this is, it's a meromorphic quasi-Jacobi form of weight 1 and index. And then, sorry, almost holomorphic, and then this guy here will be the quasi. And essentially, these two guys, G2 and A, are all that you need. In some sense, the only two examples that you need. So maybe to give you a third example, then there's also this theorem of Littgruber that tells you if you have any M is any compact manifold, complex manifold, then the elliptic genus here is also quasi-Jacobi form. Of weight 0 and index given by this dimension m divided by 2. And so here, I mean, quasi-Jacobi form again with this character that we have to include if you're manifolds. Actually, this theorem is not hard to prove. Okay, so I'm raising. Are there any questions?
So for Calabi-Yau, it's Jacobi, and for general, it's quasi-Jacobi.
Yes.
Is it clear what in the deviation from Calabi-Yau makes it quasi? Can one understand this?
You mean what's the holomorphic anomaly of this elliptic genus?
Yes.
Yeah, I looked into it and I never found any nice answer to that question. Yeah. And it's true that if you start with elliptic genus of some manifold, you can look at the dependence on this A or this G2, and you can ask what, and you don't have a dependence on A, you just have dependence. No, you have a dependence on A, but no dependence on G2. You can ask the dependence on A, and then, but it's not clear to me. Yeah, it's a nice question. I also. So let me check the time. Okay, so maybe I just explain the proof of this theorem because I thought about it. Where do quasi-Jacobi forms appear? And basically, there are two main places in the literature. One is as the elliptic genus of a complex manifold. Second one is in Gromov-Witten theory. And so the theorems here is actually easy to explain. So let me just give you a quick sketch. Okay, so this elliptic genus here, I wrote it down before, let me just write it down again. This is this product of theta of xk divided by 2 pi I minus z divided by the theta of xk over 2 pi I. And so you can normalize this here, put in this theta of minus z factor, and then take out this theta of minus z to the dimension of m. So this is a complex dimension. Yeah. And then this was already discussed last time, that this on the right hand side you get the Zagé function. So there was the Zagé function. F tau of b. Let me write it as x comma z. So theta of x comma z. And here I take my convention of theta. This theta here is this theta 1 divided by theta.
Maybe you should multiply by the derivative.
Yeah, this is what the eta 3 is, the derivative of theta. So otherwise it's the same after maybe factor of I or something. Okay. And so the idea is just expand this f tau in this variable x. And so how do you do this? So let's say, and what you really want to expand is f tau of x comma zeta, you multiply it with x. So the theta function has a 0 and x equals to 0. So theta of x has a 0 and x equals to 0. So this f tau of this has a pole at x equals to 0. If you multiply with x, you remove that pole. So this starts with 1. So what you really want to take the extension of is the logarithm. Logarithm, let's call the function fl times the x. And so now the claim is that FL is Jacobi, so it's meromorphic. Jacobi of whatever, where L index 0 is 0 for A bigger equal to 2, and is quasi-Jacobi. 1 is quasi-Jacobi. Of the same weight of example. And so how do you prove the claim? Well, let's think about the transformation properties of this f tau of x there. So the transformation properties we saw yesterday, but you can also just take the transformation properties of the theta function and then apply them. And let me just give you one example here. So we had the most complicated one was this x over tau, v over tau. And so this transformation property was the e to the 2 pi I v divided by tau f tau of x and a and b. So now if you take the log of this equation, you get log okay, so let's ignore this first of x here. I mean, take log of this one or log of this f of tau is essentially the same. So log of f, and if you x divided by z minus 1 over tau. So yeah, I can put it. Sorry, what did I do? Okay, so, and then here we have 1 over tau, and then you have x over tau, and z over tau. And you see on the right hand side, you get a sum, right? So you get the log of tau, you get plus, and now comes this the main fact. So you get x times z divided by tau times plus the log. So if you ignore this kind of this middle factor, what you see is that the only deviation from a straight equality comes in the linear terms in x. That's kind of the point. So the linear terms in x are precisely the ones that contribute to this F1. So if you expand this left-hand side now in this power series Fl of z tau x to the L, and also the right-hand side, you see the only deviation from a straight equality here comes in the linear term. Essentially, that's the proof. So F1 is positive. And F is in fact, this F1 is just our A. Okay, so in fact, F1 is just this.
Where is the compactness? Where is the compactness of that thing alone?
I haven't touched M yet.
Ah, okay.
And compactness
Because
plays a
you
role.
say it's a proof, so I think.
Yeah, the compactness plays a role because I write the integral sign. I don't want to think about equivalent channels. So I'm just now, once you have this, the proof follows because you can just you take the log of this expression, and I mean this expression is times the x of the log of this expression. Times the integral of the exponential of the log of this expression. The log of this expression is just a sum of this journal roots. Then you take the log of this function here, which is exactly this guy here. So this is the sum over the L. L bigger than 1. And then here you have FL of minus z comma tau. Then here you have this xk divided by 2 pi I to the power. And now we do what we always do, we interchange the sums. So you see the same factor exponential. That all stays the same, and then you have L bigger than, maybe I just do this here. So if you think about this guy here, what this is just the sum over L bigger than 1, and then you have FL, this term goes out, and then you have the sum of this xk. Sum of the k of the xk to the L divided by 2 pi I. In fact, the 2 pi I over L you can also look at. And then this, of course, is are the Chern characters. So this is the Chern characters. The Lth Chern character of the tension bundle multiplied with L factor. So in the end, what you get here in this expression so you get just this theta function in the beginning, and then times the integral exponential of the summation FL of minus z, and then times this Chern L times L. And so you just get a power series with power series of cohomology classes whose coefficients are some product of this FL, and then you just use this term. But you see that if Chern 1 of your tangent bundle is 0, you don't have a F1, so everything is triple. That's kind of foolproof.
And E2 never appears.
E2 never appears. Yeah, so to answer your question, if you apply d over dA or whatever, d over d, I mean, so I think as a e is equal to e1 in multiplication, and this is also our f1.
Yeah.
If you want to calculate the derivatives back to this, you just take the derivatives back to the first factor and you get something. I didn't see any structure. Okay, so I want to come to the properties of this quasi-Jacobi form. And this is a little bit I can explain some. So the first one, let's do the first one, which is the key to all of them, which is the transformation property. We have, let's say we start with a quasi-Jacobi form. The I alpha to the j. And let's say again, finally many of this phi j are non-zeros. And so the big phi, we know the transformation property. But then you can deduce it from them, the transformation property for the small ones, because this new I alpha j are algebraically independent. So you can just take the coefficient. So you can write down the transformation property for this guy here. And then take the corresponding coefficient corresponding to phi 0, 0. And what you end up with is the following function. So let's say phi is phi 0, 0 here. The following equation. And let me just write one of them, and then the other one is in the notes. So then we write a complicated one. So, and I apologize. So the first factors are the same exactly as in the transformation property of the Jacobi forms, and then you get a deviation. Namely, you get 1 over I factorial, j factorial, and you have minus c over, and these terms don't really matter. But, just for the correctness sake. J final. Okay. And this is for all in this essay. And so the way you should read this equation is that first of all, the function phi is just a constant term of kind of so you have the big function phi, which has a lot of data, and you just take out the constant term, so the particular data. But still, if you just took out the constant term and you apply this transformation, kind of get back information about the higher f phi j. And so in some sense, this phi knows also about the higher phi j internally when looking at the transformation problem. Conversely, when you know all of the phi j, you know how this phi transforms. So the upshot is, if you do this carefully, is that this constant term map, so the constant term map, this goes from the vector space of almost holomorphic Jacobi forms of weight k and index n to the space of quasi-Jacobi forms. Just sending this phi to its coefficient of nu to the 0, alpha to the 0, so phi 0, 0. It is an isomorphism. So in the definition of Jacobi forms, quasi-Jacobi forms, I said there exists one. I didn't say there exists a unique one, but this says that there exists a unique one. So I don't know who asked this question. You asked this. Does that answer the question?
Yeah. Sorry, very nice. What happens if this sum I put crazy coefficients on multiplying the phi's? I cannot do that.
You mean if I multiply the nu here?
Yeah.
Yeah, then you destroy the Jacobi form. I mean the Jacobi form transformation property. You destroy. Yeah. So if you and you see, I mean, this is a reason why. So in particular, it tells you if you this property tells you that if your phi 0, 0 is vanishes all the other also have to vanish. So if you multiply nu with your nu, then yeah, you cannot preserve that one. But yeah, this comes out of the proof. The proof is essentially using this transformation property, taking and using the transformation property here, taking all of the nu to the I alpha to the j coefficients. This gives you some system of equations solving this, and then realizing somehow that knowing this for all A, B, C, D, and SL2Z is the same as knowing this as when you treat C and D as variables. So this is some Zariski density argument. Essentially, there's pairs C, D. So there's some argument, but it's not that complex.
Is there any structure in the space of almost homomorphic?
You mean structure?
Yeah, I mean, I'm asking because this looks very similar to what happened in the theory of vertex algebras, that you can reconstruct the field from the state, this state field correspondence. So I don't know if there is.
Yeah, so I don't know much about vertex algebras. I mean, maybe I should have extended my list. So the third place where the quasi-Jacobi form comes out is also as traces of operators on vertex algebras. So that's what also. So probably there's some relationship, but I don't know. Yeah, there's work by Marzon and yeah, maybe I should also give some references here. So the main reference is the Gober. So he has, if you Google the Gober quasi-Jacobi forms, you find a paper where he discusses this, some of the theory behind this. And then there's also, at least in the way I presented here, there's a paper of myself with Aaron Dixon about Gromov-Witten theory of elliptic fibration. Elliptic fibration. Vibrations. And then I have on this. Yeah, there's also a recent paper of myself on the morphic anomaly equation. Where it's also a nice summary of this equation. So I mean, I would first look here, and then unsatisfied. Okay, so this was 1 and 2. So let me do 3 here. And in some sense, 3 we also already saw. Essentially, so we had these 2 differential operators, Q ddt, and then dg dp. And they destroyed the Jacobi form property, but they preserved the quasi-Jacobi form property. So they define operators on the algebra of quasi-Jacobi. So the d-tau raises the weight by 2, and then this guy here raises the weight by 1. And I'm saying we almost saw a proof of this because I gave 2 examples in the beginning. One was the E2, which essentially came from taking derivative with respect to d-tau. And then the second one is this A, this logarithmic derivative with respect to theta with respect to z. Essentially, if you think about this, then you see also this property. Okay, so more interesting is what I call the anomaly operator. And so, and the fact is, and this is a nice exercise, is that taking the derivative with respect to this variable nu, so nu here was our 1/8 pi of the imaginary part, and alpha was our imaginary part of z divided by imaginary part of tau. Taking the derivative with respect to nu, and then taking the derivative with respect to alpha preserves this algebra of almost polymorphic Jacobi. And so this means that you can do the following operation. You can start with this derivative operator, and you can conjugate it with this constant term map that we have on the other side. So we just
Sorry, the tau, I forgot the variables. The tau and the z do not satisfy any relationship, right? They commute or
the tau and the z, yes, because it's just derivative.
okay. Just different variable.
But of course, these ones, I will come to that. So they preserve this. So if you look at their constant term map here, you can just conjugate with this constant term map. So you can first take the inverse of the constant term map and apply the constant term map at the other side. And we call this this d over dg2. Okay, so this is a map from the quasi-Jacobi form of a given weight and index. And the constant term map, let me draw a diagram here. The constant term map maps this to almost holomorphic Jacobi forms. So you go from here to here backwards. So then you take the d over dmu. This gets you to the same space, but with weight lowered by 2. And then you go back to this. So this gets you to quasi-Jacobi forms or weight a minus 2. And similarly, you can define the d over dA, which is the constant term respect to the alpha. And this goes from here to the one where you lower the weight by 1.
Sorry, what is d minus?
So CT stands for constant term. So this is this guy here. This map that takes the almost homomorphic Jacobi form and just takes the constant.
Is there this notation, or are there actually coordinates C1, 2, and A with respect to which this is the derivative?
We say it again.
Is that this notation, like when you write d by d C1, 2, and d by d A? Is this just like some abstract notation, or are there actually coordinates C1, 2, and A with respect to which these are derivatives?
So this is G2. Yeah, so this is just notation.
It's just notation.
Just notation. But the variable nu and alpha, this are honest variables. So I can explain this notation in a second. So there are essentially 2 arguments for this notation, 2 reasons why you can use this notation. So let me say a large remark here. So the first argument you can make for this notation is that this defines your derivation. Okay, so d over dg is a derivation. On the string of quasi-Jacobi forms, because this guy is derivation, and then you commute. And moreover, and now if you take d over dg2, and this is just our formal convention on there, and you apply g2. Okay. So let's try to do this. So what I really mean by this is taking the constant term map, applying d over du, applying the constant term inverse of g2. So we have seen this is just this guy here. We've seen that G2 is the constant term of G2 hat, which is G2 plus mu. Right? So if you take the inverse of constant term map, you just get G2 plus. Now you take the derivative, you get a 1. So you get this. And similarly, things happen also for A. So if you take D over dA, this A. And so this was the reason why we chose nu and alpha in a kind of weird form, essentially to normalize this object. The second reason here is why you can choose this notation is that if you look at the algebra of quasi-Jacobi forms, it embeds into the algebra of meromorphic, Jacobi forms.
Can you say something about the algebra structure is just multiplication? There is something funny about that.
In the quasi-Jacobi forms, it's just multiplying the functions. And then if you multiply, the weight gets added and the index also gets added. And the proof is not hard, it's just from the.
It's a bigraded ring.
It's a bigraded ring. So Q dash is a bigraded ring. The index is always non-negative. And then the weight has a bound on the things. The lowest weight die is the power of theta to the power of 2m. So theta has weight minus 1, so this is 2m. So this is a bigraded. So the second fact is you can show that this quasi-Jacobi form is embedded into a subring of meromorphic Jacobi forms, where you add two free generators, namely this G2, and then this thing. So this is a free polynomial. And so this is the second. In fact, you can show the following. So you can show the following proposition. Qj is the subring of the following of the free polynomial algebra. Polynomial ring. So take the free polynomial ring generated by the following generator. So you have to include the theta function because that's just everywhere. You include the Weierstrass elliptic function. You include the derivative of the Weierstrass elliptic function, and you include the G4 Eisenstein series, and then you include the non-Jacobi form generators G2 and alpha, which define your holomorphic functions. Define holomorphic functions. On this upper half. And the exponent of theta should be yes, maybe I should say theta squared. So often it's more useful to also allow character. For example, for this elliptic genus, you want also to allow the character of the theta function. So then it's easier to define quasi-Jacobi form as a subring, where you don't take a square here, just take theta. Okay, so then you also allow odd half integer index Jacobi forms or quasi-Jacobi.
Are the differential operators d tau and dz, do they satisfy some relations with the two differential operators below, or are they completely independent?
Yeah, so I have 0 minutes left, so I cannot answer this question. No, this is the last thing I wanted to explain. So there's some Lie algebra relations. So they satisfy exactly the commutation relation of the Heisenberg Lie algebra. So which is exactly also the Lie algebra of the Jacobi group. So in fact, so you can take the weight operator, which is x on this on the degree weight, the degree k part of the quasi-Jacobi forms by multiplication by k by the weight, and you also have the index, where the index x by multiplication by the index. And then you have this relationships here with dg2 and d tau to minus 2 times the weight. That is exactly the same relationship as for quasi-modular forms, where you get an SR2 action. So then d tau d over dg2 together with the weight operator define your SR2 action on the algebra quasi-modular form. That's exactly the same here. And then you can look at d over dA. How does it interact with the dz operator? And of course, the interaction of these guys here with the weight and the index are already specified by saying where they send to the corresponding eigenspace. So this one is just, so let me just check to be correct. So this is just 2 times the index. And then The interesting what happens if you take d over d2 with respect to dz, you just get d over dA, and then there's also a factor of -2. And then here, not surprising, if you have d over dA, d tau, this just gives you some. And so maybe a final remark about this anomaly operators. If you take d over dA of the function phi, so let's say phi is the constant term of some big phi here. So if you have big phi, and you take the constant term, then d over dA of this phi is just exactly phi 0, 1, and then d over dt2, and phi is exactly phi 1. Okay, so this is exactly yes. Okay, so that's all I wanted to say about quasi-Jacobi forms, and then we'll do 5 minutes break or something, and then we'll move to Gromov-Witten theory.
Okay. Okay.